Good afternoon. So let's before we start the new topic where I want to discuss a little bit about statistical mechanics. I think I said that we would take a look at this construction of the monoclinic unit cell by choosing lattice vectors slightly different manner and see if the unit cell that's going to be produced or the crystal that is going to be generated looks exactly the same. Okay, so what I am going to do now is, so this is a problem that we were dealing with, right? We were dealing with the CA-MgSi2O6, which is having the monoclinic, for which the monoclinic crystal system is appropriate. Okay, so we have the lattice constant A, B, and C given to us, and how do we actually choose the lattice vectors? And we know beta should be given here. Okay, beta is for this problem, the beta was some 103.98 or something like that. If you looked at the MATLAB file, you would know it. Okay, so the first, what we are going to do is we are going to not generate the entire crystal structure. I'm going to choose two basis atoms, one at 0, 0, 0, the other one at 0.3, 0.1, and 0.8, and show you that no matter how I choose my lattice vectors, the position of this point relative to A, B, and C, this will correspond to the A lattice vector, this one will correspond to the B lattice vector, and 0.8 is going to correspond to the C lattice vector, right? So no matter how I choose my lattice vectors, I will show you that this will be in exactly the same spot, okay, relative to the A, B, and C. Okay, so first what I am going to do is I am going to choose my A along the, so this is going to be our coordinate system. Okay, the first choice is having A along x axis, so this will be my A vector, right? And then the C vector was somewhere here, it was actually on the xz plane, right, with the included angle beta, and this is our B vector, right? So now I have constructed these structures. So this is the first one. This is actually the unit cell which was constructed using these basis vectors. So as you can see, so the B is pointing in the same direction as y, right? You can see here the B is pointing in the same direction as y, A is pointing in the same direction as x, and the C vector is actually in the xz plane. Okay, it's in the xz plane, and you would be able to see it only if I rotated it. So this is actually the C vector, and it is in the xz plane. Okay, so now the question is, if you look at it from the B axis, you should see the obtuse plane, right? And so what I wanted to show is, this is the point that we are dealing with, this red color point that you can see. Can you see this point here? That is the internal point. These are the corner point which correspond to the basis 0, 0, 0, whereas this internal point is the point which corresponds to 0.1, sorry, 0.3, 0.1, 0.8, right? We need to keep that in mind so that we can check these things. Okay, so let me so looking at from the B axis. Okay, so this is going to be your C, and this is located at 0.8 C. So this would be, this distance would be 0.8, so it's kind of closer to the length of the C. Okay, and this distance would be how much? 0.3 A, and this is A. And if you wanted to see the corresponding distance in B, you would have to rotate it in such a way that the B is perpendicular, is along the plane of the page. very slow. So this point right here would be at point 1b. Okay, from here if you measure the distance to this point, it will be point 1b. So I am not able to move it here because it is exceedingly slow. Okay. Now similarly, figure 2, I have used a different choice of the lattice vectors. In this case, I have made the A vector lie along the xy plane, okay, A cos beta. So it is going to look more like this is still z. Okay, so this would be our C vector, this would be my A vector, and that would be the included angle beta. Okay, A is actually lying in the xy plane and Z would correspond to the B vector. So I have just chosen the lattice vector slightly differently when compared to what we did in the previous choice. This was the first choice and this is the second choice. If you look at this as well, it's possible for us to see that so my B is about the z axis, so I am viewing it from B and I am able to see the obtuse plane, right? And then this is my C, this is my C direction, and clearly this distance is 0.8, right? It is kind of closer to the end of C, right? And this distance is how much? 0.3, right? This distance is 0.3 because this is going to be along A, okay? And if I view it from the, if at all this thing lets me, yeah, so this one is B, right? This is 0.1. So no matter how I actually choose this, the coordinate system, how I choose the lattice vectors with respect to the coordinate system, it is possible for me to generate the same crystal as long as I am careful. Remember, we need to associate A with the x fractional coordinate, B with the y fractional coordinate, and Z with the and Z with the Z fractional coordinate with the C vector. Okay, so we need to associate A with x, B with y, and C with Z. As long as you are consistent there, it does not matter how you are going to choose these lattice vectors. So this is important for monoclinic crystal systems. This can get a little bit confusing when you are generating your crystal structures. Okay, so this is the third choice. In the third choice, I made A point in the Z direction, B point in the x direction, whereas C is going to now lie in the YZ plane. Okay, C is not going to lie in the YZ plane. So in that case also, if you take a look at it, you would still have this particular fractional coordinate lie at the correct spot with respect to each of the three axes. There would be no inconsistency. So consequently, any general position, if you are going to generate, it would lie at the appropriate spots. It may not look the same. You might have to make some additional effort to make sure that the crystal systems look the same if you are using different set of lattice vectors. Okay, when you use the MATLAB code that I just gave you, it is not really apparent. That is why I had to use this to demonstrate this. But when the lesson is, as long as you are consistent with associating your A vector with x, B vector with y, and C vector with z, and choosing these lattice vectors in the Cartesian coordinate system will not really affect the manner in which your crystal is actually built. Okay, but the other ones are pretty straightforward. Orthorhombic and tetragonal, all these things are straightforward because they have an included angle of 90 degrees, and it is quite obvious how these crystal structures should be generated. But for some of these things, it can be a little bit confusing. Okay, so this is viewing it from the B axis. This is beta, and about the C it is closer to 0.8, and about A it is closer to 0.3. So this would be 0.3, and then if I rotate it further, you can make sure that it is just 0.1 in the Z direction along the B axis of the B lattice vector. Okay, yeah. Yeah, yes, it is similar to saying that the reference axis, the Cartesian coordinate system XYZ axis, and the crystal ABC axis are different. and you can in any way you want. You can choose your reference in any way you want. Yes, that is the point that this exercise basically demonstrates. While it is obvious for the other crystal systems, this can get a little bit confusing. So I thought it might be useful for us to take an example and show that it does indeed not change things quite a bit. It's okay? Any questions before we proceed? Okay. Sure. But do you have any questions so far in what? Okay, good. So now I am going to start doing something, the next part of the course where we start talking a little bit about statistical mechanics. Statistical mechanics, like I mentioned in the previous class, is a subject by itself, and you can take several semesters worth of courses to understand this course very deeply. Okay, our purpose in this course is not really that. Our purpose is to talk a little bit about statistical mechanics to show you that it is because of the framework of statistical mechanics that molecular dynamics simulations actually work. And some of the expressions that are used to actually calculate properties of materials after you have conducted a molecular dynamic simulations are in fact coming from the framework of statistical mechanics. So it is a good idea to actually know some of these basic principles when we are trying to run molecular dynamic simulations, so that we know what this simulation is actually doing. Okay, so that is the goal of this particular module of this course. So I won't go in great detail discussing all the results of statistical mechanics, but hopefully just provide enough ground so that when you are actually looking at some expressions that people have used in order to obtain properties of materials, you should actually know that these are coming from statistical mechanics, and there are rigorous ways by which these can be derived, and you should know how to use these expressions to calculate these properties, and not necessarily always have to derive them from the fundamentals. It may not be always possible. Okay, so that is the goal of this part of the work. Okay, so many of you might already have some introduction to statistical mechanics or statistical thermodynamics per se, right? Enough in your material science courses, they might have dealt with it in some detail. So some of this might be a little bit repetitive, so bear with me. So overall, statistical mechanics provides a connection between the macroscopic properties of matter and the microscopic constituents of matter. Okay, so what this macroscopic means and microscopic means is something that we will come to in a little bit in more detail. But to give you some idea, you can say that temperature is basically a macroscopic property of a given system. Pressure is a macroscopic property of a given system. So is Gibbs free energy, enthalpy, and all these things, all these thermodynamic. When you think about thermodynamics, there is no more information that is available to you as to how that particular quantity is actually related to the things that actually make up the system, right? So if you have atoms making up the system, thermodynamics is not telling you how the positions or the velocities of these atoms is actually related to temperature or pressure or Gibbs free energy or enthalpy. Okay, the idea of statistical mechanics is to provide this connection. That's it. Okay, and it can be quite involved in trying to see how this is obtained. So thermodynamics, like I mentioned, it just provides the relationship that exists between various thermodynamic quantities, right? So you all have seen several such relationships. For example, it tells you that maybe rate of change of entropy with respect to the internal energy at constant number of species and volume is equal to, what is it? Dou S by dou U. Maybe 1 over T, right? How would you do? You all seen this thing? Plus what? What else will come here? Material science students? Chemical potential. Mu dn, right? So we need to know a little bit of this thermodynamics if you want to appreciate statistical mechanics somewhat. So now if you wanted to look at what is, so let's try to write down this relationship. So you see that I'm keeping volume as a constant and this number of species as a constant. So I am going to say du is equal to TdS or dou S by dou U when volume and number of species of the material is kept a constant. I get this thing called 1 by T, which is temperature, right? So this is classical thermodynamics, right? Classical, you must have studied it in mechanical engineers or material science. All of you would have studied these equations at some level. Okay, some of you might have looked at chemical potential, some of you might not have looked at chemical potential. That is the only difference, right? So thermodynamics is not doing anything beyond this. And this is another relation, right? This is another relation which is interesting to look at. Dou E by dou V at constant N and T minus temperature times dou P by dou T at constant N and V is nothing but the negative of pressure. It's possible for us to prove this relationship as well. Okay, let's not worry how this comes about. You can prove it. Okay, what is important for us to note is thermodynamics does not really worry about what the system is actually now made of. This relationship holds true whether it is consisting the system as one atom or two atom or hundreds of atoms, right? This is a relationship that thermodynamics can give you, and it does not make any explicit assumption concerning what the constituents of matter are, right? So it only says what minimum number of properties are required to describe the system. You all must have seen that, right? If you have can somebody highlight that? The minimum number of properties that is required to describe the system. So we always talk about things like, what is that called? Gibbs phase rule or Gibbs phase rule, right? So if you have one single phase, a single constituent system, you need only three things to actually describe that system, either NVE or NPT or something like that, right? So those are basic thermodynamics. We won't go into that. We'll assume that some of that is known to you all. Okay. So if you know that, you can basically derive other quantities that are there in thermodynamics. So that's thermodynamics. Now statistical thermodynamics is not doing that. It is going to assume the existence of atoms and molecules, and it can provide explicit expressions for the macroscopic thermodynamic quantity like temperature, pressure or energy, etc., etc. And it is these expressions that we are going to use in molecular dynamic simulations to get these properties. Okay. For example, if you have a system comprising of a large number of atoms, okay, at a particular temperature T, and all of them are interacting with each other through in some way, then okay, let us say it's not interacting with each other. So maybe an ideal gas, argon gas, is there inside this room, right? And the entire room is actually isolated from the surroundings. So it's an isolated system. And if somebody asked you, how would you calculate the internal energy of the system? What would you do? What would be an expression that you would instantaneously write down in order to tell me the instantaneous, the kinetic energy of the internal energy of the system? Is nothing but the sum of the kinetic energy of all the molecules, okay, assuming that they are all not interacting with each other, right? So that very statement is connecting this concept called internal energy to something that is associated with each and every atom that is there in this box, right? It is connecting the velocities of each and every atoms in this box to the macroscopic thermodynamic quantity called energy, right? So it is in this spirit that statistical mechanics is capable of providing you with expressions for the macroscopic thermodynamic quantities from the microscopic constituents of matter. Okay. So like I mentioned at the beginning of the class, the goal is to be able to appreciate why computational methods like MD and MC are working, how we can use these expressions once we run a MD simulation. This is very important. So this not be perturbed by expressions arising from statistical mechanics expressions when we see them in a technical article, right? It is not always possible to rederive all the equations of statistical mechanics to be convinced that these can be used, right? It's impossible, it's probably not possible. So we need to be able to at least know where these expressions could have come from and how we can actually use it without knowing its detailed derivation, right? If necessary, we should be able to follow some derivations as well. Okay, so this is actually the spirit with which I want to present the statistical mechanics portion of this course. Okay, there are more deeper courses that you can take in statistical mechanics, and I think you should probably take them if you want to learn more. So let's start a little bit with some basic ideas of statistical mechanics. So let us begin with considering a volume V. Okay, suppose we have a volume V. Okay, and it's completely isolated. I always like this isolated things, makes things very easy. And it consists of n particles. This entire volume is V, and this entire thing is in energy E. Okay, there are n different particles here. Okay, so macroscopically we have actually specified the system completely, right? Like right now I just said that a thermodynamic system can be specified completely using three variables or three things. So N, V and E completely specify the macroscopic state of the system, right? Macroscopic state of the system. However, at the microscopic level, the possibilities of specifying something called as a microstate is just huge. So what that essentially means is the energy E of the system can be realized in so many different ways. Okay, specifically the total energy E is nothing but Ni times epsilon I, right, where Ni is the total number of particles with energy epsilon I. Okay, so you can just add them all up and you can get this energy E, right? So there are now it should be apparent that there are so many different ways this energy E can be reached, right? Each of the particles can be put in different energy levels so that the total energy of the system is E, right? So in order to illustrate this, let me take an example just to see what this means. Let us say that our particle does not contain more than the total number of particles is just 3. So there is P1, P2 and P3 are the particles. They are identical in every aspect, but I can distinguish them. Okay, that means I can one is maybe marked with some yellow color, and other one is with blue color, the other one is with red color. Okay, and the total energy of the system is something like 6 joules. Okay, and I am going to say that they cannot take energy 0 or any decimal energy. All integral energies only they can take, these particles, just for the sake of illustrating what these many ways of getting this energy E means. So one way of getting this 6 is have all of them have the energy of 2 joules, right? 2 plus 2 plus 2 is 6. That is one way.
Sir,
Yes.
in this example, are you considering the system only has kinetic energy, no interaction between particles?
No, in this system, so the question is, in this example, am I looking at, so now if I want to look at some other way by which this particular energy of 6 joules is reached, one other way is say maybe 1, 3 and 2, 2, 3, 1, 3, 1, 2. Is there anything else? 3, 2, 1 maybe, and so on. 1, 2, 3. Okay, 1, 2, 3. Then what is that? Okay, 2, 1, 3. Huge, huh? Large number of ways. There are quite a few number of ways in which you can have one particle at energy level 3, one particle at energy level 2, one particle at energy level 1, right? Then is there anything else that I can do? 4, 1, 1, then 1, 4, 4, then 1, 4, 1. Is that it? Sorry, very sorry. This is 1. Okay, this is 1. Then this is also 1. Anything else? Any other possibility? No. Is there any other way by which I can get 6 joules from 3 particles? 510, no, because I am not allowing that. Okay. So when we saw this distribution, okay, we saw that there are different ways of getting some energy. There are different ways of realizing this macro state. There are different ways of realizing this macro state. Each of this state is called a microstate. This is one microstate. This is another microstate. This is another microstate. Okay, this microstate, one particle has energy 3, other particle has energy 2, other particle has energy 1. This one is 2 particles have energy 1 and 1 particle has energy 4. It is very clear that there was one particular state which had the maximum possible number of ways of achieving it. For example, this 1, 3, 2 combination, you had 1, 2, 3, 4, 5, 6 ways of achieving that, whereas only 3 ways of achieving this and only 1 way of achieving this, right? So if this were a real system, okay, then the likelihood of you at any given instant of time, the likelihood of you observing it in this microstate is higher than the likelihood of you observing it either in this or this microstate, right? Yes or no? Right. So it so happens that when you have extremely large number of atoms, like what happens in a real material, when the number of atoms or the number of molecules or the degrees of freedom that you are dealing with is in the order of 10 to the power 23 moles of atoms, then there is going to be one specific microstate which is so large in number, this number, okay, this is called as the microstate, or the total number of microstates, or the complexions, number of complexions, number of ways you can actually achieve this particular microstate. Okay, when you have a large number of atoms, this number is going to be so large that you are going to be seeing it when you examine the system. Okay, 99.99999% of the time you will see that all the other systems, all the other complexions or other microstates do occur, but they occur very rarely and you hardly observe them. Okay. But that doesn't mean that the system cannot take that microstates. All the other microstates are also equally probable. They are going to occur. Okay. But you will observe this because this occurs very, very frequently. Okay. This is an example of 3 particles, some energy 6 joules of energy. We just took it just to illustrate. Basically, this was done to illustrate 2 terms. One is a macrostate and microstate. Okay. The microstate is incommensurate with the applied macrostate, right? Each of these are the same macrostate, right? NVE, the energy is 6 joules. It's not different. So there are microstate, each of this is a microstate, and then what you specify is a macrostate. The macroscopically using thermodynamic variables, what you specify is a macrostate, and the ones that you specify microscopically by looking at the number of ways you can actually achieve this macrostate is called as a microstate, okay, or number of complexions.
Don't you need to specify the temperature for this system, why is N, V and E sufficient?
So why is N, V and E actually sufficient, and you don't need pressure and other things? So the question is, why is just 3 sufficient? So that is actually a deep question. We need to look at Gibbs phase rule to actually answer that question. We will consider that for a single phase material with consisting of one type of atoms, one type of species. It's enough if you have just three variables specifying the state of a system. But look, let us look at it from basic thermodynamics. You have seen this expression, du is equal to TdS minus PdV plus mu dN. Have you seen this before? Yes. So what is dou U by dou S at constant V and N? It's temperature. Okay. So in this expression, it is viewed as if this ds is a controlling variable, and the corresponding thing that turns out or comes out of it is actually the temperature. Okay. In this expression, it is viewed that dV is actually the controllable variable, and the pressure that comes out of it is actually the result of it. So dou U by dou V at constant entropy and N is actually minus pressure. So they are conjugate variables. You don't specify both pressure and volume at the same time. Specifying one will automatically determine what the other one is through these relationships. That's the answer for it. If you are going to specify everything, like for example, if you specify N, V, E, you can't do it independently. You can't specify the temperature here independent of the entropy of the system. You can't specify the N independent of the chemical potentials of the system. You cannot specify the pressure independent of the volume of the system. They are all related.
So if I cannot specify the temperature,
although macroscopically you have specified a certain set of parameters N, V and E, it is possible to achieve this through in many ways. It's possible to achieve this through many ways, and each such way is actually called as a microstate, corresponding to a given macrostate of the system. Okay. Now, the question is, the nice thing about the statistical thermodynamics is, if you knew this omega, the number of ways you can achieve a particular given macrostate, if you have an explicit expression for that, it apparently seems to be sufficient for you to derive the entire thermodynamics of the system. Okay. Now, how, instead of worrying about how to calculate this omega, which we will come to in maybe 1 or 2 classes, I would like to show you how, if you knew this omega base and making only one single postulate, okay, we will show that the entire thermodynamics will actually follow from it. You will be able to see all the expressions that you saw in thermodynamics based on this omega instead of the thermodynamic parameters. All the thermodynamic parameters can in turn be obtained from this omega, and omega is nothing related to thermodynamics, right? It is related to the number of ways this thing can actually reach a certain energy, number of ways you can arrange this system so that a particular energy is obtained, right? So omega is actually a number, is some large number. Of course, it depends on your N, V, E, okay, but it is going to turn out to be a number at the end, some large number for a system that is comprising of a large number of atoms. So in this case, all these were omegas, where the total number of complexions that you can actually obtain in order to reach a particular macrostate. Okay. So what we will do now in order to show that is as follows. So we will consider a system there are two systems here. So this one consists of N1, V1, and this has energy E1. This is N2, V2, and energy E2, and both of them are isolated from the surroundings. Okay, and for now they are also isolated from each other. Okay, so we say that, so clearly from our previous discussion we can say omega 1 N1, V1, E1 is a total number of ways the system here, the A1, this is the A1 system and this is the A2 system, which are both isolated. The total number of ways A1 can have this macroscopic state. Total number of ways. Okay. So here N1 and V1 actually don't matter, it is only the energy that is going to be of importance to us. So we will not necessarily write them. Okay. Omega 2 is the total number of ways the A2 system can actually have the macroscopic state N2, V2 and E2, right. Now we are going to do a small experiment. What we are going to do is, we are going to say that this central wall that is right here is going to make both the system A1 and A2 come into thermal contact with each other, right. They are going to come into thermal contact with each other, but the number of the species don't move around or the volume doesn't change. It's not a piston movable piston, it's just something that will allow the exchange of energy alone. Okay. The question that we now ask is, when will the exchange of energy stop? If something is different about these two, because of this the energy has to flow. What is it? Temperature, right. There's something different about it, because of this the energy has to exchange, and that thing that is different is what is going to drive the energy to move from one system to the other. And it will happen according to classical thermodynamics until when? Until their temperatures are equal. So until T1 is equal to T2, this exchange of energy is going to happen. Okay. So this is from thermodynamics, we already know it. Okay. That is a known, proven statement from thermodynamics. So there is nothing we question about it. So we want to see if we can have such a relationship, or if a relationship similar to this can be attained without actually invoking temperature.